welcome back to this sixth session, sorry, in this series of seminars. Today in the field of energy, concretely electric energy, with a talk related to challenges and opportunities of distributed generation in cities. So the talk will be done by Lorenzo Olivieri. Here you can see him. He's an associate professor here at UPM. He's a member of the Distributed Renewable Generation and Intelligent Control Group. Is a member of the Solarenergy Institute and is also a member of the Center for Innovation and Technology for Human Development. Lorenzo has been working since long ago, long, it depends on the hair we have in here as always, but since long time in there, in energy efficiency in buildings basically, and also in the integration of renewable energies in the built environments, okay? And it's been specialized concretely in building integrated photovoltaics, and this is why the field and the seminar that we came today here, okay? So I think no more presentations for today for Lorenzo. I think we should spend the time in his talk and also in the questions afterwards. So Lorenzo, please, whenever you want, the floor is yours.
Okay, thank you, Alvaro. Good morning, everyone. I'm going to share my screen, my presentation.
Great.
So, are you saying it? Yes. Okay.
Yes, perfect.
So I would like to start my talk today saying that, or remembering maybe, that we are facing a lot of global challenges nowadays in this particular historical moment. And these big challenges require a mission-oriented approach to be reached. A mission-oriented approach is a term we use frequently in these last years. But what is exactly a mission-oriented approach? A mission-oriented approach is an approach based on concrete, measurable, challenging, and achievable goals that needs to activate innovation across sectors of different actors, fields of knowledge, and between also academics with industrial sectors. So it's an approach that looks for activate and to promote the innovation between the interaction of different actors. And following this approach, my mission as a researcher, as a teacher, is reducing carbon emissions of city. How can we reduce the carbon emissions of cities? Making that our cities, making that the cities look like some examples we will see forward. So the classical example of a mission-oriented approach is just the Man on the Moon mission that was announced in 1960 and was reached on 1969. To reach this goal, this incredible goal, was a lot of knowledge from different fields, a lot of interaction between different researchers and industrial actors was enveloped. And we have a mission that maybe it's less romantic than the going to the moon, but that it's equal or more important than this old mission. And so, as I said, from my point of view, we have some solutions to promote the reduction of CO2 emissions in our cities. As you can see in these pictures, I'm showing a lot of PV systems of different photovoltaic systems integrated in different kinds of buildings on the roof, on the facade, integrated on the parking lots, for instance, and also integrated on public areas that nowadays, today, are not used in a big way to produce electricity. So let's see why are we focusing why are we focusing on cities? Because we know that more than half of the world population lives in cities. Cities consume about 3/4 of the global energy, use it worldwide, and also, but not also cities could create policies and measures fast to be put in action, to be implemented much more faster than, for instance, policies promoted by national councils or international level. You can see here Madrid 360 is an example of this power of the cities to promote some policies to reduce, for instance, the access of the city center to the vehicles that produce the most of the contaminations or the pollutions in cities. So this is simple an example of the possibility of cities to implement in the real world the policies that sometimes are very slow to come from the higher levels of the governance institutions to the real facts. So it's clear that cities are the core of the global climate change mitigation. And the question is, what can we do to make them more compatible with our planet? This is a simple question, but the answer obviously is not simple. In this presentation, I will talking about distributed PV generation as a tool to reduce the emissions produced by cities. First of all, I would like to clarify why are we speaking about distributed generation? Which are the advantages of these models in comparison with the centralized model we are used the most today? The first of all is that distributed generation can improve the efficiency of the energy system. This is very intuitive to understand that if we produce the electricity we use on the roof of our house or our office or on the facade of our building, we are improving the efficiency of the overall system. Think for a moment what happens with the food we buy to live. We are aware that if we buy an apple that have been grown in proximity of my city, I'm reducing the emissions of the food sector. And we need to make the same thing with energy. Energy cannot be a thing that comes from away, but it needs to be a thing we can produce closer to the closer to the loads. So this is clear that we can improve the efficiency of the overall energy system if we introduce more distributed generation systems. The second point here is that to mitigate climate change impacts, it's much more relevant distributed generation than centralized generation. I'm referring here not only on the reduction of emissions, but on the resilience of the system. We can think, for instance, that the frequency of extreme weather events like tornadoes, like heat waves, like extreme cold waves, etc., are going to the frequency is going to going up in the next year due to the climate change. So the distributed generation systems are more robust compared to the centralized system, because if we can generate near the loads, we can control of the elements that can that can work well or not work well. So we are providing a much more safe energy system from the point of view of the energy supply. And the third reason is because distributed generation has greater social impact than a large centralized a centralized system with very big power plants. The centralized power plants, or the big power plants, can be designed and constructed only by the very big companies that can assume the investment required to build discrete power plants. But this does not occur with distributed generation. A small system can be designed, can be built from small companies, in a lot of cases family companies, and this big number of companies has a bigger social impact on the country, improving the numbers of companies, the numbers of jobs related with the model we are using to produce electricity. So I think the reasons why the advantages of the distributed generation are clear. Let's move on to justify why I'm focusing on PV generation. The first one is that solar energy is the most distributed energy resource that we can use today. So it seems logical that if we are promoting a distributed generation system, we have to use a distributed energy source to implement it. And you can see in this map that we have a very wide access to the solar potential worldwide, and we can use this technology in very different latitudes and very different sites worldwide. The second reason is that PV is one of the clearest and cheapest way to produce electricity today. We need solutions today, not within 10 years or within 15 years, because we are we need to reduce emissions today to mitigate the effects of the climate change. So let's see some numbers to justify this sentence. In this graph, you can see the life cycle GHG emissions of different technologies used today to produce electricity, and values are expressed in grams of CO2 equivalent per kilowatt hour produced. As you can see, PV is on the right side of the graph, and the values ranges between 9 and 80, less or more, CO2 grams for kilowatt hours. And on the left side, you can see the other technology used today to produce electricity, for instance, central based on hard coal or natural gas, or with different solutions, with carbon capture and storage, or without carbon capture and storage, but the numbers in these cases are always much more higher than for PV. On the right side, you can see that wind power has a lower GHG emissions compared to PV, but obviously it's not so easy to integrate wind power in the city, because wind power is based on moving blades. It produces noise. It's based on very big systems of very big wind turbine normally. So we can say that for the built environment, the best technology, or the less the technology that we can use to produce electricity with a low impact is photovoltaics. And about cost, you can see in this graph that nowadays, not within 10 years, nowadays in most of the cases, producing electricity by photovoltaics is the cheapest way we have to produce electricity in general. You can see on the left that the metric we are using to compare different technology is the realized cost of electricity, and euro cents for kilowatt hour, and PV is always, or in the most cases, the cheapest way to produce electricity. So these numbers justify that we have today about 760 gigawatts installed overall in the world, but the grid number is that about 20% of this power was installed in 1 year, last year in 2020. So this is a market that is growing very fast, and it is growing very fast because it's cheap to produce electricity with these systems. And also, I would like to highlight that the share of the distributed PV generation is increasing in the last years. You can see here that the PV systems, not all of them are distributed systems, because we have also a lot of PV plants, but the numbers of rooftop installed systems is increasing market share. So this is a good news, because the distributed model is improving its weight in the market of PV. Another reason is that cities' electricity demand will increase in the next years, and will increase in the next years due to two main factors. The first one is the electrification of the mobility, with the diffusion of the electrical vehicles, but we have also to take into account the electrification of the heat, based mainly on the use of heat pumps for heating in buildings in general. These is the two main reasons for the increase of the electricity demand in cities. So we need a technology that produces electricity in city without improving the emissions of the cities. And also, I would like to highlight that PV can be extensively used in human settlement, because it's the safest source of energy we can use today. And to explain this point, we can have a look at this graph. You can see here the death rate from accident and air pollution of different energy resources used to produce electricity. This metric is measured that's per terawatt hours of energy production. So you can see that it's very different. If we produce electricity using coal, I would like to say that coal is nowadays the most used energy resource to produce electricity worldwide, with about 40% of the total. And we have a death rate of about 25 deaths per terawatt hour of energy production. Solar energy only has 0.02 deaths per terawatt hours of energy production. So we can confirm that solar energy is safe for human life. And also it's safe for the planet life, as you can see on the right side with the greenhouse gas emissions of these different technologies. And last but not least, PV can be beautiful. We live in Europe, we live in very beautiful cities. We cannot renounce the beauty of our city to produce energy, to produce electricity. And look at this example, for instance. This is a school. It's in Copenhagen. It's an international school in which a PV facade has been integrated and has been integrated with a very high levels of design and aesthetics. Aesthetics in general of the building. Several planes has been used to integrate the modules, and we can see that we see different colors due to the different angles we see the models. So in this kind of systems, we are speaking about building integrated photovoltaics, and you can see in this other example, this is a mountain hut in the Alps. The PV element replaces a conventional construction element. We are not adding PV modules to the building, but we are designing the building with PV elements. It's a very different thing. And you can see that the building envelope is not functional without the PV element. So the BIPV element is multifunctional. This is very different from the system we see most frequently in our cities, in which conventional modules are used. The building envelope is fully functional without the PV modules, and the PV modules only generates energy. So if we compare both solutions, you can see that obviously there are a lot of differences. And it's like to compare Champions League on the left side with the amateur league of my town in the right side, from the architectural point of view and from the quality point of view of the integration. I'm not saying that we have to only integrate PV we have only to do BIPV systems. We can do also added systems. It's not a problem, but I think that we have to spread the use of BIPV system in our cities. And we can do it because there are a lot of solutions in the market nowadays to convert our passive buildings into small power plants, simply using different materials that are not being used nowadays in a very diffuse way. And another thing I would like to say is that there are a lot of a good number, a lot maybe not, but a good number of specialized companies. And most of them are European companies. So we have a very good opportunity to spread these solutions in Europe. So that's it. We have the solution for the energy transition. It looks, it seems that there is not problem to go to promote the transition in our cities. Maybe it's maybe it's sure, but for the moment we are far away, because if we look at how we did how did we get the electricity from last year, we can see that if we only look at the electricity system, only 2.7% was produced using solar technologies. And if we look at the big picture of the total energy system, including the transport and the heat generation, so the number is as low as 1.1%. So we have a very long way to do to improve this number, to increase the share of this technology in the different markets. So what are the challenges and the opportunities of distributed generation in cities? From a point of view, to increase the BIPV diffusion, and I think that we have to teach in the architecture school and also in engineering schools how to use these systems to design building with PV technology, and not to look at this system as added system to convert the building into a generation or a small power plant. So this is a very important point. And also it's very important to take into account that it's very that renovation projects are as important as the new buildings we are building today. And energy renovations that do not incorporate PV generation are, in my opinion, missed opportunities to move faster toward climate neutrality of our building, of our cities in general. And with BIPV system, we can reduce the energy needs of the building as typical passive refurbishment project, insulate, like to improve the thermal performance of the envelope, of the glazing, etc. But BIPV also allows on-site energy-free electricity, on-site emission-free electricity, and also adding architectural value to the building that it's not possible with other solutions. Then we have to consider that cities are not buildings only. We have a lot of spaces that are not being used today to produce emission-free electricity that can be used. For instance, the parking lots, as you can see in this image, in this photo, and we cannot. We have to use of the possibility of generation in our cities, because our cities are very energy intensive. And in the same line, there are a lot of public spaces that are not used, and that can be used to produce electricity with photovoltaics. And in this sense, I think that there is a very big interest on adapt concentrator PV to the built environment. Concentrator PV are a specific type of PV systems in which an optical part is used to concentrate the sun into small PV cells that are very efficient. So this technology has been used in large power plants, but can be used also can be adapted to be used in the built environment. And the main the thing here, the most interesting thing is that, as you can see, these systems has a very small footprint. In our cities, we have small surfaces in general to generate electricity, and the surface is very expensive, is extremely expensive. So technologies that like this one that can generate big amounts of electricity with a small footprint are very interesting to be integrated in our cities. We have recently worked on a research project to adapt concentrator PV to the built environment. You can see here the results of this product. Is called Power 3. It's a high concentrating photovoltaic system installed on an element that has much more features than a conventional CPV systems. We have integrated lighting system and also nature-based solutions to improve the air quality in the urban environment. I would like to show you a video about the systems, about the Power 3. Let's see if it's work. No. Yeah, maybe. Okay. Okay. So you can see in the next year we are going to see a lot of this kind of adaptation of other technologies from other fields. For example, for the big power plants to be integrated in our cities. And I think that this is a new field of research in which we need the knowledge from engineers, from architects, from botanics, from a lot of different field of knowledge to decide to build effective solutions. So that's all from my side. Thank you very much for your attention. And I would like to answer questions.
Okay, thank you very much, Lorenzo, for this nice talk. And as always, you could do some questions, just raising your hand, just opening the mic, or even on the chat. So do as you wish. So let's try. We have some minutes with Lorenzo to punch. Yeah.
If it's possible, I would like to ask you about, should we be afraid about, because as we all know, we have a big problem with the crisis with the minerals, rare minerals. will it be a big problem? Because we need too many rare minerals for producing the solar panels, no?
Well, really, the bigger part of the PV modules is silicon. It's a very distributed resource, and in general, we need different other minerals to build the module, but in a very small quantity. So at the moment, there are a lot of problem of supply of a lot of products, for instance, chips, for instance, copper, I know, but at the moment, there aren't problems of supply of PV modules because there are not so there are not used a lot of minerals that are not available today. So maybe in the future, I don't know, but at the moment it's not the case. For batteries, different. For instance, distributed generation is in distributed generation. Sometimes we have storage systems, and storage system use much more minerals that are not available today, and so it's possible problem in the next years.
Okay, thank you.
Any other question? We'll start breaking the ice a bit more than Lorenzo. From my point of view, you saw like something that it's quite hopeful, but discouraging at the same time, because it seems that there's a long way to work on it. But I mean, we are in a good position. We have the tools, we know we have the technology, but everything seems complex to reach it, you know? So, and when you saw all these examples of building integration with the PV panels, the BIPVs, it's kind of strange to me that why it's so. I mean, what there are more BIP systems in our cities. We are supposed to be quite fancy stuff. We build in nice houses. We put in modern houses with the panels. So why there is no so much of it?
Well, I think that there are different barriers to increase the share of these solutions in the market. One of them is the lack of specific training of young architects and young engineers in this specific kind of systems. We are speaking about of systems that has a direct effect on the thermal loads of the building, for instance, the lighting loads, depending on the type of the integration, also on the electrical design of the system. So the problem is that each of these fields of knowledge are not, each one is like close area, but we need professionals that know of different things, that knows the quality of an architectural integration, but also the physics of the PV systems and so on. So it's a quite new market, and actually there is not a specific training for young architects and engineers. For instance, in my school, I'm teaching a course about integration of BIPV in our cities, in buildings in general, but for 3 years, for 3 years, and I think it's a short time to see the effects in the market of these new kinds of systems. Architects and engineers has to know how to implement this solution in their projects, and not to look only for it when he or she has to reduce the impact of the building, reducing the CO2 emissions and so on. So I think one reason is this one. And also another one reason is that when you compare, for instance, a PV glass with a conventional glass, obviously the PV glass is more expensive, the passive solution, but the PV glass will generate electricity along the life of the building, and you have to take into account the incomes produced by this system. You cannot compare different things with the same metrics without taking into account the different incomes produced by, for instance, a PV glass in comparison with a passive conventional glass. So sometimes, if we look only at the price, obviously there are cheaper solutions. But if we look at the lifetime of the building, these solutions are much more competitive. I don't know. I think this is the two main reasons that are reducing the spread of these solutions in the market.
And I mean, it will be any energy, how to say, power generation issues also in this time. I mean, it will be better to get an integrated PV system, or it will be better to, I mean, not from the static point of view, but just from the energetic point of view. Will be any difference of the modules that we use are the same? How all these things work?
There are some differences because to improve the aesthetics of the modules, sometimes you have, for example, to change the color, and the color has an effect on the efficiency on the module, or you have to reduce, for instance, or you have to use some coatings on the front side of the module to hidden the PV cells, so you are losing production. But in this case, we have to compare it with a conventional element, not photovoltaics. So sometimes you have to compare. For instance, I can do a curtain wall with aluminum solution, or I can do it with PV elements. The PV elements will generate energy, less energy than conventional PV modules that are being designed only to produce electricity and energy, but will produce much more energy than an aluminum cover of the facade or aluminum system. So in this case, sometimes we reduce the efficiency to allow the use of these elements in high-level projects. But I think that, as I said, we cannot pronounce the beauty of our cities. I cannot think living in a city covered of PV modules, because obviously it's not the best architectural effects that you are doing, that you are creating. So there are a lot of different things to take into account, and maybe this one is the main problem of this technology, to become a mainstream technology in the architectural field.
Okay, thank you, Lorenzo. So great. Thank you very much, Lorenzo, once again. And see you all next couple of weeks in a fortnight. Bye bye.
Thank you so
Bye.
much, Lorenzo.
Bye.
Bye.